Our goal here is to write a polynomial knowing what its roots are. Now, I've told you several times that the roots of a polynomial are like the DNA of that polynomial. So if I know the roots, I should be able to figure out a function that has those roots. And sure enough, we can. Here's the steps. There's really only two of them. Start by writing your polynomial in factored form. So start with an f of x equals or with a y equals. And now we're going to take these numbers, turn them into factors. To do that, let's remember that I want to put this in for the variable for the x and have my factor be 0. So if I have a negative 2 for this x and I want a 0 as the result, then I need to add 2 to make that happen. Negative 2 plus 2 is what would give me a 0. Similarly, for this factor, it's going to be a plus 1. And then for this last factor, a minus 3. The shortcut version, if your factor is negative, have a plus. If your factor is positive, have a minus. That's the important part. The rest here now is just making sure we can multiply things out properly. This is called the factored form. We're now going to get what is called the standard form. So pick two of them, doesn't matter which two, and we're going to begin by multiplying those together. So I'm going to set myself up a little grid. I've got an x plus 1 and an x minus 3. Multiply to fill the boxes. Okay, then. So we haven't dealt with the x plus 2 yet. I'm just going to leave that alone. But when you multiply these two together, you get an x squared. 1x minus 3x is minus 2x's. And then the minus 3 on the back. Next up, let's do this one more time. Now take the x plus 2 times that trinomial we just got as the result of the first multiplication. Now, the grid this time, going to have 3 spots in one direction. So I've got an x plus 2 and an x squared minus 2x minus 3. So x to the third minus 2x squared minus 3x. 2x squared minus 4x minus 6. If you organize your work this way, it really makes putting your terms together nice and easy because your like terms are on the diagonals. So my final function here is going to have an x to the third. Makes sense, I hope, right? If there are 3 roots, I should end up being degree 3. Negative 2x squared plus 2x squared, no x squareds. Negative 3x minus 4x is minus 7x with a minus 6 on the end. This being the 21st century, I would like you to pull up a graphing calculator and check it. If I think that this is supposed to have roots, x to the third, at negative 2, negative 1, and 3, then I should see a graph that crosses the x-axis at negative 2, negative 1, and 3. Important to know, this is not the only polynomial that has these roots. I could, for example, multiply all of these terms by 2, and the roots wouldn't change. Or multiply all of these numbers here by a negative 4, and the roots wouldn't change. So we are finding the simplest polynomial function that has those roots. But if you really wanted, you could multiply then by any number, any constant number in all the terms, and get the same x-intercepts each time. Okay, let's go again here. When there are fractions involved, it is only a little bit more complicated. So let's take a look at this one. So from this factor here, I've got to ask myself, if I want 4/5 to be the answer, what should the original factor have looked like? So let's just work it backwards. Let's multiply the 5 over. And if I wanted originally to be equal to 0, subtract the 4 over. There's what the factor should look like. Now, if you figure out some shortcuts to get there quicker, I'm all for it, because there are some patterns you can take advantage of. But for this to be a root, this is a factor that would get us there. Now, if you wanted instead just to write x minus 4/5, you can. You're just going to have to work with fractions in your multiplication, which makes it a little tougher for a lot of us. So I think this is maybe a better way to go. From the 3, that's going to be an x minus 3, and then from here an x plus 1. Okay, here's what I'd like. Would you go ahead and do a little pause? I want you to multiply this out, and then we will compare in a little bit. And then for this multiplication, I actually am going to write out my grid here because there's a lot to keep track of. Okay. So I'm going to end up with 5x to the third, negative 10 and negative 4 is negative 14 x squared. Negative 15 and 8 is minus 7x's with a plus 12 on the end. Let's check it. I want negative 1, 3, and 4/5. That's 0.8. So yeah, we're in good shape. Now again, this is not the only one. If you had, say, 10x to the third minus 28x squared minus 14x plus 24, if all the numbers are doubled, same roots. If you multiply all of them by the same constant, you're still going to have the same roots in the end. And I hope it makes sense why. Think about why that would be. Okay, last one here. Once again, I would like you to do a little pause and then unpause when you are ready to check things. So let's do a midway check here. Make sure we had the same roots. So here I'm going to end up with 2x plus 3. Here I'm going to end up with 2x plus 5. And here I'm going to end up with 3x minus 4. If you're not sure where those factors are coming from, please do a quick check-in with a neighbor or with me. Okay, let's then do some multiplying. I personally like to leave the one up front alone and start from the back. This is a little tougher to do in my head, so I'm going to set my grid up again. Got a 2x plus 5, 3x minus 4, so 6x squared plus 15x minus 8x minus 20. So 6x to the second, 15 minus 8 would be 7. Then with a minus 20 on the back. Okay, gonna move you out of the way so that I can make a new grid now for this second multiplication. So a 2x plus 3. Okay, 14, 40. And then here, that'd be 18. 7, 3, 21. And then 23 minus 60. All right, let's now put the like terms together. So 12x to the thirds. 14 and 18 is 32, x to the seconds. Negative 40 plus 21 is going to be 19 negative, negative 19, and then a minus 60 on the back. Let's give it a check. X to the second plus 32, whoops, x to the third plus 32x to the second minus 19x minus 60. So there's my -5/2, my -3/2, and my 4/3. So we have the roots where we need them to be. I just want to wrap up with tying this in with the previous discussion. Notice that how each of these examples had 3 roots. That's why we ended up having a degree of 3 in each of our final answers. That's that fundamental theorem of algebra coming back.